Alrighty, so here's the deal. We're going to talk about if I have a machine learning model, specifically a machine learning model that does binary classification. It takes in an input data point, like about a person or about something, and then spits out a binary classification of they have the disease or they don't. This is a cat or this is a dog. This is correct or this is incorrect, something like that. If we have a binary classification problem and we have a machine learning model that will solve that problem for us, we want to think about how good that machine learning model is. And when you try and figure out how good it is, it gets a little bit nuanced, how we define that. And how we define it really impacts how we train our model and what kinds of models we get, because that, how we define how good that model is impacts how what we optimize for when we're training. Okay, so the basic idea is when you have a binary classification model, there are 4 different types of outputs you could have. So in this example, we're going to be doing imaging data. So it looks at an image from like some kind of diagnosis scan, like a biopsy something, and diagnoses whether the model thinks that someone has cancer or not. And this is a real world application of these machine learning models. So this is a binary classification problem. So the model will take in an image and will predict either that person does not have cancer, this negative, or that person does or might have cancer, and you should do more tests. And then on this y-axis, we have whether the person actually ended up having cancer or whether they did not actually end up having cancer. So true positive and true negative is where you want to be. Either they didn't actually have cancer and you caught that, or they did actually have cancer and you caught that. And these two, false negative and false positive, how good or bad they are kind of depends on what use case you are. False negative means that the model said there was no cancer, but there actually was. So that's really bad. And false positive is the model said that there was cancer, but there actually wasn't, which probably wastes some time and resources, but is not the end of the world. And you could have other applications where, for example, a false positive was worse than a false negative, and so you care more about that. Okay, so the most basic way of measuring how well a model does is once you calculate those numbers, the true positive, true negative, false positive, false negative, then you plug it in and ask, okay, just like how many of those were correct? Accuracy is, they say, it's a very blunt measure of model correctness, because it's literally just take all of the predictions that were correct over the total number of predictions, and that's your accuracy. Now that is great for the most part, but the problem is if you have a data set that's very unbalanced. So in our disease example, let's say that maybe we have 95% of the data points are from people without cancer, because more people don't have cancer than have cancer. So if 95% of our data set is of healthy, no cancer patients, but then 5% of the data set that we're training our model on are patients who do have cancer, well, then there's a problem here. And that's that if we're optimizing for accuracy, our model could just always say that someone doesn't have cancer, and then it would get 95% accuracy, which is quite good by most standards. And so you can see in the diagram here, if the model always predicted negative, they never predicted positive, that's why these are both 0, then they would get 95 true negatives and 5 false negatives, which is a completely useless model, but gets quite good accuracy. And so the overall idea is that accuracy works fine for if our data set is balanced. That is, there's about equal numbers of like actual positive and actual negatives in our data. But if it's unbalanced, then it starts weighing more heavily towards whatever is more represented in our training data. So to correct this problem with accuracy, we have another metric, and this is recall. So the basic idea of recall is we're saying out of all of the true positives, so out of all of the data points that should be predicted as positive, how many did we correctly predict as positive? So on the on this confusion matrix diagram that we have here, it's all of the ones that are actually positive. So we're completely ignoring whether the false positives or the false positives and the true negatives. We don't care about that for recall. We're just taking everything on this top half of the chart, everything that's actually positive, and see how many of those were correct. So we're taking the total number of true positives over the total number of true positives and false negatives. So this is one way to think about it, but the way that I, with a more math brain, like to think about it is, notice here how false negatives is the thing in the denominator. So if the true positives, if there's 0 false negatives, the numerator equals the denominator. This whole thing is 1. That's good. We have perfect recall. The more false negatives we have, the lower the recall. So all recall is doing is minimizing, well, not all, but basically what recall is doing is minimizing false negatives as much as it possibly can. Recall is going to penalize our false negatives, which in our disease case is exactly what we want to do. If our cancer goes undiagnosed, that's a big problem. So for our cancer example, we might want to optimize for recall. Okay, and now you could have the opposite kind of thing, where maybe we want to minimize not false negatives, but false positives instead. So precision goes about this differently. It says, out of all of the positive predictions the model made, how many of those were correct? So recall that in the case of recall, we were doing all of the ones that are like all of the actual positives and calculating how many the model got right. And so we were trying to minimize those false negatives. Oops. Now for precision, we're doing something different. We're taking all of the predictions that the model made and seeing how many of those are correct. So we're instead trying to minimize those false positives. Okay, so what this looks like mathematically is we take the true positives, and the false positives on the denominator. So notice the only difference between precision and recall is this term in the denominator. In recall, it's false negatives. In precision, it's false positives, which means that here, what we're doing is we're trying to minimize false positives. So precision will penalize or go down if the number of false positives is higher. And an example of when this would be useful as opposed to recall is, say, spam email detection, where we really don't want a good email to go to spam because then it gets missed. You could miss an important meeting, but if ever so often a spam email comes through to our inbox, like, it's not the end of the world. So for spam email detection, maybe we care more about precision than we care about recall. But of course, for most problems, you kind of want a balance of both. You don't want really terrible recall. You also don't want really terrible precision. Like, you don't want to just have a gazillion false positives, which optimizing for only recall might give you. You also don't want a gazillion false negatives, which optimizing for only precision might give you. And so the outcome of this is we can kind of balance the two with something called F1 score. So F1 score takes something called a harmonic mean, which is some fancy math thing that I don't understand, of both of the precision and the recall. So you're basically balancing both. So what's important to note about F1 score is that it penalizes having bad precision and it penalizes having bad recall. So if either precision or recall gets really close to 0, since they're multiplied here in the numerator, this harmonic mean, F1 score, is going to go to 0 as well. And then we will be sad. So this helps us maintain a balance of like pretty good recall and also pretty good precision. And notice how both neither recall nor precision depend on the data set being balanced like accuracy does. And so that's why F1 score, which balances both precision and recall, is often better than a better measure of how good a model is than accuracy. And this is very commonly used in real-life machine learning applications. All of these are. So it's good to know their pros and cons. And in checkoff, for this pset, we will ask you to dissect, based on the tectonic data set, what kinds of metrics would be best suited for the data that we're given.